right, welcome back, team. We're now looking at section 1.6, absolute value functions. To help with absolute values, we need to understand what it represents. The absolute value of x represents the distance from 0. Okay. So you can think at it as the distance on a number line from 0. And remember, distance is never negative. That's why the absolute value is always positive, because it represents distance. If you have the absolute value of, let's say, x minus a, then that's representing the distance from a. So let's consider the example below where we want to list two numbers that are 3 units away from 0. Well, here's our 0 here in the middle. Well, we know the number 3 over here to the right is exactly 3 units away from 0. But there's also another number that is 3 units away from the 0 on the left, and that is -3. Funky looking brace there. So that's why if we were to take the absolute value of 3, we would get 3 because it's 3 units from 0. Likewise, the absolute value of -3 also gives us 3. So let's consider the absolute value of x equals 5. Now we know that the number inside that absolute value either represents 5 or -5, okay? So one way of looking at that is that the inside number equals 5, or that inside number, the opposite of that number, equals 5. In other words, it's representing the positive version or the negative version. So when solving absolute value equations or inequalities, I'm going to show you a way that works for both. We have two possibilities. So remembering that an absolute value on the inside could be a positive version or a negative version helps you to remember that you're looking for two possible solutions and also how to look for those solutions. Okay, so let's take a look at this example here. We're going to look at it algebraically first. So we want to solve the absolute value of x minus 4, that quantity being greater than 2. Well, our first option is that the inside is the positive version. So we can think of it as distributing a positive 1 to the inside, and that being greater than 2. And when we solve for that, we distribute the positive, nothing changes on the left. We can add 4 to both sides, which doesn't change our inequality, and we get x is greater than 6. Great. But the second possibility is that absolute value is representing the negative, the opposite. So we're going to distribute a -1. So if we do a -1 times the entire inside of the absolute value, that will give us the opposite of x plus 4 is greater than 2. We're going to subtract 4 from both sides, so we get the opposite of x is greater than -2. And remember, when you divide by a negative number, and we'll write that little note here, when we multiply or divide by a negative, switch the inequality. Okay, so don't forget that old rule. It still goes into play, even though we may have learned it in 5th grade. It's still true today. Okay, so if we divide both sides by the -1, we get a positive x less than 2. So if we're looking at it in terms of the number line, we know that we need our x larger than 6. So let's see, 6, we're going to have to extend this a little bit. So we need our x larger than 6 and an x smaller than 2, all the way out here. Now, when we look at the original equation, this means the distance from 4 is larger than 2, right? Absolute value represents distance, so the distance from x to 4 has to be larger than 2. Well, if this is our 4 right here in the middle, there's 2, so it has to be larger than 2. Over here on the left, that 2 is 2 distance away. So we're going away from the number 4. So we end up with 2 intervals as our solution. So the left interval, we're going from -infinity to 2, union, and then we pick it back up from 6 to infinity. Remember, since our inequality is strictly greater than, there's no or equals to, then nothing's included. Everything is in parentheses. Now, not all absolute value equations and inequalities are going to be like this. We may have to do a little more manipulation. So let's take a look at example 2 here, where we're solving 3 times the absolute value of 2x plus 4, that quantity, minus 1 less than or equal to 8. Before we can do our 2 options, we must isolate that absolute value. So let's add 1 to both sides. And that will give us 3 times the absolute value of 2x plus 4 is less than or equal to 9. Then let's divide both sides by 3. And so we get 2x plus 4, that quantity is in absolute values, less than or equal to 3. Now we can do our 2 options. Option 1 is the inside is the positive version. So we get a positive 1 times 2x plus 4 is less than or equal to 3. So 2x plus 4 less than or equal to 3. Subtract 4 from both sides. We get 2x is less than or equal to -1. And then divide both sides by 2. We get x is less than or equal to a -1/2. Now we do the second version. Our second possibility is the inside is the negative version. So we're going to distribute a -1. -1 times the quantity of 2x plus 4 less than or equal to 3. Distribute, and we get a -2x minus 4 less than or equal to 3. Add 4 to both sides, we get -2x less than or equal to 7. Now when we divide by the -2, our inequality is going to change. And so we get x is greater than or equal to a -7/2, which if we're going to graph that, that gives us a -3.5, kind of gives us an idea of where it is. And now we can graph the solutions on the number line so we can determine where our interval or intervals lie. So our first one was that x is less than a -1/2. So here is a -1/2 less than or equals to, moves it to the left here. Our second possibility gave us x is greater than or equal to a -3.5 or a -7/2, which is here. But that is greater than or equal to, so it shifts to the right. You might look at it and go, oh, well, it's all real numbers because we're going to end up graphing everything. But let's take a look at our original equation here, where we're looking for the values of x that will give us a distance smaller than 8. Or if you want to look after we get the absolute value by itself, we're looking for a value of x that would give us a distance smaller than 3. So you're actually looking for an interval around certain numbers. So in this case, we look to see where these two intervals overlap. And they overlap here between the -3.5 and -1/2. So you can leave it as -3.5 if you want to, but recall that we have a less than or equals to. So that means we're going to use brackets to show that our endpoints are included. -3.5 all the way to a -1/2, both endpoints are included. All right, so the next couple of examples here are kind of unique. Notice the example here on the left. We want to solve an absolute value that is less than -1/2. What this is saying is the distance from a -8, because we don't have the subtraction, is less than -2. So here's our thought here. We cannot have a negative distance. So this guy here is no solution. There is no x that if I took the absolute value, I would end up with a number less than a -2. But notice in this problem, the absolute value is already isolated. So let's say if I had a -2 absolute value of x plus 3 less than a -1, we cannot make that decision here because I haven't isolated that absolute value. Once I divide by -2, I get greater than a +2. That's doable. So we can't make the no solution decision until after we've isolated the absolute value. The next problem here to the right, we're asked to solve the absolute value where it's greater than -3. So again, this is saying the distance from a -4 is larger than a -3. Well, all distances, right, are larger than -3. Than any negative, actually, than a negative. Because remember, your absolute value would always give you a positive number. Positives are always larger than negatives. So any value of x from -infinity to infinity would work, okay, for all real solutions, or all real numbers, I'm sorry. So let's now remind ourselves of what the absolute value function looks like when you graph it. It's a nice V, okay? Some people confuse it with a parabola, but remember a parabola is curvy, whereas this guy comes to a point as that sharp corner. You have points 0, 0, 1, 1. So you have a slope of 1 to the right. You have the slope of -1 to the left. And when we say parent function, that just means the basic graph before any transformations. You're not adding, subtracting, or multiplying to shift or reflect the graph. We're wanting to graph a couple of transformations based on that original parent function. So let's focus on this one to the left. We know it's an absolute value, but what does this new function tell us? The negative on the outside of the absolute value, we had it just like this. That means we're multiplying a negative by all of the f of x values or all of the y values. So that means we are first going to reflect about the x-axis. The second thing is when we're adding that 3 inside to the x. Remember, those inside changes works opposite the way we think. So when we add a 3, we're actually going to shift left 3 units. And the last thing is we're subtracting 2 from the entire function. So that means we are going to shift down 2. Okay, so a couple of things. When you're doing some of these transformations, it might help to do them one at a time or group them, but you need to know what the parent function looks like. So if we were to regraph the parent function, I'm going to do it here just in a dotted blue. And multiplying all of those output values, in other words, all of the y's by a negative means it's going to flip over the x-axis. So flipping everything downwards, our graph is going to look like that in purple. And now we can shift all of those points left 3 and down 2. So I'm going to do that final graph in black. So I'm going to start at my origin here, and I'm going to shift it to the left 3 and down 2 right there. And my next point on the left, I'm going to shift it left 3 and down 2 here. And if you remember, we haven't really stretched or compressed anything, so all of those slopes are going to be the same. So we can just keep going here, down 1 over 1. And we can do our final graph in solid. So that's been reflected about the x, shifted left 3 and down 2. Now in this graph, they're asking us to do something slightly different. This time they've given us the picture of the graph and they want us to determine what the original equation is. Well, we can tell by the shape of the graph that we are dealing with absolute values because the shape is a V. So if we were to graph lightly here what a parent function of an absolute value looks like, okay? Again, parent function would be f of x equals the absolute value of x. Then we need to see how this graph has been manipulated or transformed to give us the other graph in blue. Well, first of all, it does not look like it's been reflected, right? It's not going over the x-axis or opening downwards. And even if we reflected it across the y, we would get the same graph back because it's even. So there's no negatives being multiplied. But then we also look at whether or not this guy has been stretched or compressed. Well, looking at the original V, it definitely looks wider than the second V to the right. So notice in this first equation here, in the first original parent function, it goes over 1 and up 1. But in this new function, it goes over 1 and up 2. If there was no stretch or compress, it should have landed here over 1 up 1. So instead of going to 1, it's going up 2. That means we've stretched the y values, because it's going upwards, we've stretched the y values by a factor of 2. So in our new function, we have a 2 being multiplied by the entire function, original function. I'm not finishing that absolute value because we might be doing more manipulation. And then we need to figure out if this guy has been shifted left, right, up, or down. So on this, I would again focus on points that we know. For example, the tip of that V and the tip of this V. How did we get from the origin over to 3, -2? Looks like we have shifted to the right 3 units and down 2 units. Using our knowledge of transformations, we shift right 3. That means we're actually subtracting 3 from the inside X value. When we move down 2, that means we are subtracting 2 from the entire function. Now, there are 2 ways that we can actually check this. We can use a table, and we can plug in values for X. For example, if I plugged in 2 for X, I get 0 for Y. That's a true point right there. If I plugged in 3 for X, I would end up with a -2 for Y. That is correct. So you can test it to make sure, or you can also graph it on your graphing calculator. The last concepts I want to cover in 1.6 are zeros and intercepts. So remember, intercepts are points. Okay, and so when we say points, you know, it's got an X value, Y value, input and an output, where the graph touches or crosses an axis. So if we think about the X-axis, in order for a graph to be on that X-axis, the Y value has to be 0, right? Otherwise, if the 0 is 1, it would go up. It's -1, it would go down, so forth. So an X-intercept is always of the form X and your Y is 0. Likewise, for the Y-intercept, in order for it to land on the Y-axis, your X value has to be 0. So a Y-intercept is always of the form 0, Y. In other words, you put in 0 for the other variable. Zeros, and you're going to hear that word a lot, are values of the input, okay, which we often think of as X, that make the function value for Y equal to 0. That's why they're called zeros. So really, when you're finding zeros, you're also finding X-intercepts. When you're finding X-intercepts, you're finding zeros. So basically, zeros are the X's of X-intercepts. So if they're asking us to solve for the 0 of a function, like in this example below, that's basically saying, suppose our Y, or the f of X, is equal to 0 and solve. So we're going to solve for an absolute value just like we did with the inequalities, but this time it's an equation. We want to get it by itself, so we subtract 7 from both sides. We get -7 equals a negative absolute value of 2x plus 3. We divide both sides by that -1. So we get 7 equals the absolute value of 2x plus 3. And now we look at our 2 possible solutions. So the first one, the possibility that the inside is the positive version. So if we distribute a +1 to the 2x plus 3, that should equal 7. So we get 2x plus 3 equals 7. Subtract 3 from both sides. So 2x equals 4. Divide both sides by 2. X equals 2. Second possibility is the inside is the negative version. So we're going to distribute a -1 inside the parentheses, 2x plus 3 equals 7. When we distribute the -1, we get a negative 2x minus 3 equals positive 7. Add 3 to both sides, negative 2x equals 10. And divide both sides by -2, and we get x equals -5. Notice I didn't put a number line here because we're not looking for intervals. Interval notation and all that shading is only when we have the inequalities, greater than or less than. If you have an equal sign, don't even use the parentheses or the brackets. You can use braces if you want. -5 and 2. And you only use the braces if you're just listing all the values. Otherwise, we could just write x equals -5 and 2. All right, that's it for 1.6. If you have any questions, don't forget to email me or come and see me during my office hours. See you soon.